Okay, so we figured out the arctangent of the y component, 2, which is divided by 3, is equal to 33.69 degrees. I wanted to convert this. This is wrong. It really would be bad form to write this like this. The reason why this can be related to cosine x and sine x was because we used infinite Taylor series expansion, and you cannot use degrees in that because this is not unitless like radians are. So this is the translation formula, times pi divided by 180. So this is really the correct way to do this would be putting 0.588. That's pretty close approximation. This is bad notation too. Put the I after 0.588i because this just looks better. The first way I wrote it, I wouldn't consider wrong. Also, how come I didn't just bother doing this? 2 divided by 3, go to my switching thing here, and I go to radians, and now I do the arctangent in radians, and I get 0.5s. So basically, when you're doing the arctangent of this to figure out what theta is, use your radian button, and then you won't have to do this. More homework problems for you. Another one that's pretty easy. I think they want us to find the absolute value, which is the modulus of 2 minus 3i. What is this? Well, this is going to be 2 squared plus minus 3 squared square root. Why didn't I just write this as 2 squared plus 3 squared square root? Well, technically, this can be written as 2 plus minus 3i. This is the a plus ib. And you'll notice that the I is in a different place. Don't freak out. This is technically correct. Are the answers different? No. A lot of times, though, as you get into more and more advanced mathematics, making sure that your notation is actually correct. If you're writing papers and doing research is absolutely vital. So, and once again, okay, so what is this? 4 and 9, this is the square root of 13. And you'll notice that this is kind of, so this was just in the book. And this one, both of these were in the book. You'll notice that the modulus of both these are the same, but they're different complex numbers. So this is important. Obviously, there's an infinite number of complex numbers that will have the same modulus. Is there anything more interesting going on here? Give a counterexample. So, this is some good stuff here. It says, give a counterexample to this. Z plus W, the modulus of Z plus W does not equal the modulus of Z plus the modulus of W. So let me see what the exact directions are here. It says, give an example of complex numbers Z and W such that the two aren't equal. So give an example. This is a great problem for you because we're starting to get to a point in mathematics where you can't just memorize stuff and put it back out. How do you figure out stuff like this? Well, you got to kind of hunt and peck. But so what I would like to suggest is that you start simple. Let's let Z equal 1 and W equal I. And this would really be 0, and this would be 0 plus I. Now let's just see what happens. So this is 1 plus I, Z plus W, modulus. This would be 1 squared plus 1 squared square root. This is the square root of 2. The modulus of Z is going to be 1 squared plus 0 squared, which is, of course, 1. The modulus of W is not 0 squared plus I squared. Remember, this is really 0 plus 1i. Here is b. So this is 0 squared plus 1 squared. This is 1. So what do we have? The modulus of w plus z, and I wrote it wrong, it's z plus w, is equal to the square root of 2, which is not equal to 2, which is 1 plus 1, which is equal to z modulus plus w modulus. And what they wanted you to understand is that in general, when you add complex numbers together, it's not, the modulus of added complex numbers is not the addition of just the moduli themselves. Moduli, does that work? Yeah. Why is that though? Think about why that is. And this is an important question. Remember when we were adding these complex numbers, they're vectors? Well, what did we figure out we were doing? So we want to figure out what we're doing. In general, if we add these complex numbers, the norm of that, or the modulus, or the absolute value, which different books will use, does not equal the sum of the absolute values. And let's understand why that should be true from just the picture. And I'm just going to make this up. Suppose we're doing this vector addition, and we'll make this the vector v, and I'm going to add the vector w right here. Well, remember what we do. We take, so what is v plus w? And you'll notice that even these are, although these are complex numbers, they are essentially vectors in the plane. So what we do is when we add vectors together, we take the tail of w, and this is called the head, this is the tail. We lift it up and we place it on the head of v using the parallelogram law. And I'll try and draw it as best I can. Okay. And then according to this addition plan, here is the transplanted w. This is now the new vector. This is v plus w, right? Now, think about what happened. We have a right angle in here, right? This is, it should be the case that, so the norm of v is the length on this side. So it should be that the norm of v squared plus the norm of w squared should equal the norm of this, which is v plus w squared. This is just Pythagorean, right? And look at what they were, basically what they were trying to show is that this isn't true. This is true. The more that you work with these, the more that you'll like these. We're starting to run out of time on this one, and I'm not sure. Oh, okay, so 2 cosine 4 plus I sine 4. So they want us to figure out to write this as a plus ib. 2 cosine 4 plus I sine 4. We're going to run short on time. Okay, well, you know what? We got to reload. We'll come back and do this problem. We're just going to keep going because this stuff's too good.